Alrighty, so we're going to look at some steps here for attacking Atwood machines. How the heck do these work? So hopefully now you've gotten the idea that an Atwood machine is really just two or more. We'll look at one that has three actually soon. Masses, they preferably are unequal masses. And because of kind of some uneven distribution of kind of gravity, really, we're going to have this system move in one direction or in another direction. So it really has to be kind of unequal in some way, because think about it. If we had two that are the same, really the force of gravity pulling down on both is going to be the same, and it's not really going to do anything, right? We won't have anything kind of exciting happening. And so what we first want to do, and what you'll have to do, is you actually have to choose a direction of rotation to be positive. And so we'll try both ways today, but I'm going to say that the positive direction is counterclockwise. So that means it's going in kind of that direction, would be the positive direction. Now, we know looking at this just right now that if we have a 3 kilogram here and 1 kilogram here, the thing is going to go in this direction. Absolutely, you're correct. And so what that means then is overall the system is going to be moving in the negative direction, because if positive is really going this way, it's going to be going opposite of that. So we'll be going in the negative direction. Now, aside from that, typically these questions say kind of find the acceleration of the system, or they go, what's the tension in the string, or they go, what's the tension in different spots, things like that. And so really, we kind of want to start with a big picture. And one of the things that I hope we're comfortable doing now is just labeling the forces. So if I wanted to label the forces on M1 here, I'd say, well, wait, we have the force of gravity on 1, and we also have kind of the tension, all right, that's acting here as well. Now, for our unit right now, we're going to assume that this pulley in purple here has no mass, it has no friction, there's no resistance. And so later on, and you'll kind of see this later, that means really that the tension is the same everywhere in the string in this setup. Now, kind of similarly, we can see that, oh, well, mass 2 actually has, well, gravity pulling on it as well. And it also has tension kind of pulling up on it as well. And the tensions here are equal. We'll talk about why in a little bit. One thing I want to note, though, is if the positive direction is going this way, oddly enough, that tells me then that this force of gravity is in the positive direction. Okay, because it's going kind of down and counterclockwise in this way that I've just shown here. But oddly enough, this force of gravity, since it's also going down, it's going in the negative direction, because it's not going in kind of this counterclockwise path here. And so even though both of these are pointing down, this one's in the negative direction for mass 1, this one's in the positive direction for mass 2, because we have to choose a direction really of rotation here that is positive, and I chose to go counterclockwise. Now, really, the thing that's going to make this all go kind of in this direction, though, we know it's really going to go that way, kind of clockwise, is this difference in mass. Again, because we said if M1 was 3 kilograms, well, 3 and 3, they're going to kind of have the same force of gravity. It's just going to be a whole lot of boring sitting here. And so really, we have to look at step 1, and step 1 is really going to be kind of just looking at what the net force is. The net force is equal to this difference in mass. So I'm going to write mass difference, and then times the pull of gravity, or the gravitational acceleration on it. And so what that means here, well, is we have a difference in mass. Well, 3 minus 1, that gives me 2. It's the extra 2 kilograms here getting pulled down that's going to make this all move. So we'll have here 2 kilograms times, well, 9.8 meters per second squared. And that's going to give me a net force of 19.6 newtons. So we know what the overall force that's making this whole system move is. Okay, then for step 2 here, we really can use Newton's second law in just a different sense, knowing that not only is the net force like this remainder, kind of whatever's the leftover force, but it's also equal to the mass times the acceleration. And so we know the net force, so we'll end up setting this left side equal to that 19.6 we had right here. But we also have to keep in mind which mass it is that we're talking about. Is it this one that's accelerating? Is it this one, M2, that's accelerating? Or is it the whole system itself? Because they're attached by this rope, and we're assuming the rope is massless and is infinitely strong and doesn't stretch, that's going to mean that this has to be the total mass. Everything's moving together. It's not just this one moves and this one kind of stays in place. That's ludicrous, right? So really, what that's going to look like then, now that we kind of have the net force here, is we're going to just write this out. We'll kind of fill in kind of a way that most people will like. I'll just say my 19.6 newtons. That is my net force here. That's equal to my total mass. Well, 3 plus 1, that's 4 kilograms. And that's times the acceleration. Well, poof, I can just do some quick division here. This gives me that I have an acceleration of 4.9 meters per second squared. That's my acceleration. Kind of neat, right? Now, what direction's that acceleration in? Well, it's not going clockwise, it's going counterclockwise. And so this would be a point where you could, in fact, add on a negative sign right there, and you'll go, oh, hey, well, the acceleration's in the negative direction. That makes total sense. Perfect. If you are like, whoa, I wouldn't have spotted that, you can totally tack it on later, and I'll show you that in just a moment here. So we found the acceleration. We've taken care of half the question. We know that. So now, how the heck do we get the tension in the string? Well, to find the tension, we have to look at just one of these objects, okay? We just have to pick one. It really does not matter which. I'm going to choose to just look at mass 1 because it's just right here. It's a little closer to home, I guess, for me. And so if I want to do that, I have to look at the net force now acting on just mass 1. So really, I only have two forces. I have gravity here, and I have tension. And kind of like with our elevator problem, we have to think about which one's bigger. Well, if the whole thing is accelerating downwards, that means if the acceleration's downwards, the net force is downwards. That means that the force of gravity has to be larger in magnitude or size than the tension force itself. So I would write this out as my net force. I kind of rewrite this. So I would say here really that my net force on 1 is really equal to the tension force. That's the one going up, which is kind of counterclockwise, which is my positive direction, minus, that's my force of gravity, that's going opposite this direction of rotation. So that's why I'm putting a minus sign here, Fg1. And that's equal to, well, mass 1 times its acceleration. We already know the acceleration, though. We'll just end up funneling this in right here. That'll be really kind of quick and easy. But now, if you didn't put the minus sign here, you would have to put the minus sign here because we're thinking, again, the acceleration has a direction. You only have to keep track of it in one of these instances because if you put the minus here, you don't want to have a minus and then a minus. You're going to have a double negative, and that's not correct. It's just the true fact that because we chose this way as the positive direction of rotation, that the acceleration of this down is going to be, well, in the negative direction. So either or, I usually just kind of put the signs on when I write my symbolic equation. That's when I find it the most convenient. So I'm going to erase my minus sign right there. So with this now, I know that force of gravity is just m1g though, and we know m1, and we know a, so we know every single thing here except the force of tension, which is pretty sweet. So all I'll have to do is I'll just rewrite this, and I'll say then that the force of tension is equal to Fg1 minus m1a. Now I can plug in my values for it. I get that my force of tension is equal to, well, m1 times g, that's this 3.0 kilograms, times my 9.8 meters per second squared, minus m1. So that's going to give me, again, my 3.0 kilograms, times this 4.9 meters per second squared. And so in the end, what I get from this is I get that there's a tension force of 14.7 newtons. That's what I get as my kind of final answer here. So we found the acceleration, ta-da. We found the tension force, ta-da. And now what I want to do actually is take a peek and look at this from the perspective instead of object one, this kind of mass one, the big gray dark one here. I want to look at it in terms of mass two. We could totally look at it in terms of that guy instead. And so the only thing we're changing here is this step 3. That's where I had to just pick one and look at it. And so this first step would be the same. The net force is still due that difference. The acceleration is still due to the same thing. We do the same step. But if I wanted to instead look at this guy, M2 instead, here's kind of how we would do it. So I'm just going to do a little squiggle here. So whoa, that was a little weird. Let's get rid of that there. So again, we still would have steps 1, just to repeat really quick. Step 1 would be the same because the net force is still due to the same difference in mass. It's that extra 2 kilograms on this side. We still would end up having that same net force kind of being right here is equal to our total mass times the acceleration. And we still are going to end up having the same total mass here. And so if the total mass is the same and the net force is the same, we're still going to have the same acceleration. So steps 1 and 2 are the same. Now this step 3 though, well, we'd want to look at the net force on mass or object 2. So we're looking over at this guy instead. And so what that would look like, well, we still have tension going up. We still have gravity going down, just like we have tension up and gravity going down on mass 1, object 1. But now this tension is going up. It's going up this way, which would be kind of opposite. So now we're going to actually have it going in the negative direction. So we'd have negative the force tension, and then gravity's going down, but down in this case really is counterclockwise. So we're going to have plus Fg2, and that's equal to, well, mass times the acceleration. And so in the end, well, we still have the mass of object 2, so m2 times a. But again, if it's accelerating up, well, that's going clockwise. That would be in the negative direction. So we're going to have negative m2a right there. And so again, working with this to get our tension alone, well, I would add this term over to this side, okay? And then I would add tension over to that side to get tension alone. So I'd end up having m2a plus fg2 equals the force of tension. And so if we were to look at the kind of do the math for that one, well, the mass of this one is 1 kilogram. So we'd have 1.0 kilograms times our acceleration, which is still this 4.9, because we would do the same step, 4.9 meters per second squared. And then we're going to have plus now Fg2. I know it's a little odd because we're actually adding it now because the force of gravity is going in this counterclockwise direction, so it is in the positive direction. So we're still going to have the 1 kilogram for this object over here, object 2, times gravity, now 9.8 meters per second squared. And so when I add those up, I actually end up getting 14.7 newtons. And so in the end, it does not matter if I chose to look at object 1 here to find the tension, or if I chose to look at object 2 and find the tension. I literally get the same thing, and it's all based on the fact that we just have to stay consistent with whichever direction we chose to be the positive direction, okay? Now, to kind of pull this all together, so like, wait, what the heck are these steps here? How do you phrase it? Well, these actually are the steps. This is something I would like you to actually add to your notes. And so really, the whole thing is we start with this big picture view of the whole system. We're going to pick a direction of rotation or motion, really, that's positive, and we just have to stick to it. Then we have to kind of keep in mind that the net force is due to gravity on the difference in mass. That's really what it is. It's the difference in mass or if we're looking at something like that ticker tape timer lab, whatever the only hanging mass is, right? So in the case of this example, that difference in mass is 2 kilograms on this side. And so that's what we did with step 1 here, and that's why it's still step 1 here, okay? So that's really step 1. Now, step 2, what I did here is, well, really we use Newton's second law. F net is equal to the total mass times A, since now this net force is accelerating the entire system. So we can use this to find either the acceleration or to find a mass, kind of depending on what we're given, in all honesty. Maybe there's a motion sensor, and from the motion sensor, there's a velocity graph, and from the velocity graph, you find the slope, and so you can get the acceleration. If you knew the acceleration and the net force, you could get the mass total instead, or something like that, okay? So that's really what step 2 is. It's go ahead, use Newton's second law with the total mass to kind of get A, or kind of use A to get M. Now, step 3 is really if we're asked to find the tension, like we were right here, well, then we just need to pick one object. It doesn't matter which. Some folks say that it tends to be maybe a little easier to look at the more massive one. I don't know how true that really is, because we did it with both here. It was literally about the same amount of steps and math and thinking. Really just pick one. That's it. And so once you've picked that one, well, if you pick the larger mass, you know then that tension is less than the force of gravity, because it's going to move down. If you picked the less massive one, well, then you know that tension is greater than the force of gravity, because it's going to be moving up on that side. So if you pick the more massive one, then, well, it has to be true that tension is less than the force of gravity, because it's going to go down on the side of the more massive object. And so with that being the case, well, we can then say that, hey, well, tension and gravity give us kind of this mass times acceleration for it. And that's really exactly what we did right here for that object. And again, you have to stay consistent with the signs of your things. Since we chose positive to be going in this direction, that's why tension is going up is positive. That's why gravity here going down is negative. That's why the acceleration is negative. If I chose to flip the direction that I said was positive, if we said, oh no, positive is going that way, well, all of these would have the opposite sign. The negatives would become positives, the positives would become negatives, okay? And so that's kind of the gist on it. As long as we stay consistent, we kind of keep using our knowledge of like looking at what are the forces at play here. That's how we kind of get these equations kind of on the spot, depending on what our scenario is. And so this is really assuming that we're going in the direction down below the larger target is the negative direction. So really saying like what I did here. But in the end, stay consistent with your directions and it will all work out, okay? So hopefully you've got this written down. We've kind of done one sample one together. And what I want to do is I've just kind of recopied and pasted the steps here kind of as reference. We can kind of take a peek at this. And I want you to try and do the same thing again, but now with this 3 object system here. So I would take a moment, pause the video, try and do like step 1, step 2, step 3 on your own. You don't need to rewrite this again. You hopefully already have it written on your page. I just have it here so we can kind of look at it a little more easily, okay? So now you've hopefully paused it. You've kind of attempted it. Let's go ahead and kind of take a peek. So just to mix things up, I'm going to say that the positive direction is opposite what we did here. So let's say that the positive direction now is clockwise, and let's kind of see how things go, okay? In the case of this one, we have a 3 kilogram and a 1 and a 2. Well, really, the 2 isn't going to make it go one way or another. It's just kind of sitting here, making it more challenging to move. The 3 kilogram is the thing that's going to make it want to go down, though, okay? And so it's going to end up going down on that side. So looking at step 1, start with a big picture, choose your direction for it. I don't know if I wrote that here. And then the net force is due to the gravity on the difference in mass. Okay, so, well, really looking at this, our step 1 then would just be saying that our net force is equal to, well, this mass difference times G. So I'm going to rewrite that. Well, the difference between 3 kilograms and 1 kilogram, that's 2 kilograms. So I have 2 kilograms here. I'm keeping it at 1 sig fig this time, 9.8 meters per second squared. And when I put that into my calculator, I still get 19.6 newtons, okay? Because kilograms times meters per second squared is newtons. Okay, so we know the net force. Now, it's time to actually use Newton's second law. We can kind of plug in now that we know what the net force is, and know that that net force is going to accelerate not just this one, but all of them together. So in total, we're moving 6 kilograms of mass based on just this force, which is due to just the 2 kilograms of extra that we have right here, okay? So I'm going to write it out. Our net force is equal to m total, because it's the total thing that's accelerating. And then if I want to get the acceleration, well, what I would write it out as is I'd divide by m total on both sides. So I'd say my net force over my total mass is my acceleration. That's going to give me 19.6 newtons divided by 6 kilograms. That gives me an acceleration of 3.3 meters per second squared. So I already have a big chunk done. We know what A is. Terrific. So now, what if we're trying to find the tension? Okay. And here's where it gets a little tricky, because we want to just pick one of these. We want to just look at one of these objects to kind of think about what's going on here. But I want to zoom in and kind of look at this picture a little more, because we have this chunk of string right here that kind of goes to the left and down from mass 3 right here. And if we think about it, this whole kind of system is going up and over and kind of down that way, right? So M2 is actually going up. We have that M3 is going to the left, and M1 is actually going down. A little odd, I know, right? But that's all kind of in our negative direction based on what I chose for my kind of direction of motion. Well, if we think about it, this first chunk of string here, A, I'll call it A right here, it is actually pulling M3 and M2, correct? It's pulling both of those, and it has to support kind of both of those behind it. This chunk of string, B, well, really, since the whole thing is moving up and this way, well, B is really only dragging behind it M2. And so, oddly enough, what we should expect is we should find that the tension in section A is greater than the tension in section B. And that's purely because section A has both this mass and this mass that are getting pulled along. It actually has to support more behind it. While in this scenario above, there wasn't an in-between portion, okay? And in the future, if this thing, this kind of pulley did have friction and its own mass, it would actually cause our tensions to be different here, okay? But for now, that one doesn't, but this one in fact does. So let's just choose to look at, M1. Let's look at M1, okay? So let's pick M1 to look at. Okay, terrific. Now, if I want to look at M1, I want to write out what the forces are on it. So, well, we have FG1, and we have, let's say, force tension A. And then on this guy, I have FG2, and well, we have force tension B. Okay, and then we do have some forces on our kind of mass 3 here. Well, of course, we have force gravity 3. We also have kind of the normal force from that one. And my arrows should be the same size. I apologize about that. And then going to the right, well, we have force tension B, and going to the left, we have force tension A. So we would expect, hopefully, that since everything's moving kind of up and over this way, well, that then, if that's the case, this force gravity 1 has to be bigger in size than force tension A. If they're actually perfectly canceled, we wouldn't get any of this kind of exciting motion stuff. So kind of doing this just like we did with step 3 up here, whether we looked at whichever kind of one of our masses, well, we want to look at the net force that's kind of pulling on it. So I would write out here that my net force on, and let's kind of keep it so we can see everything, on object 1, well, it would be force tension A minus the force gravity 1, because gravity tension's going in this direction we said to be positive here, equals, well, mass 1 times its acceleration, because we're looking at just the net force on 1. That's really why it kind of looks that way, okay? So, and I'm not sure what this little doodad there is. Let's get rid of that. And if the whole thing is accelerating, we know the whole system's moving this way. That means that the sign for this acceleration is negative. It's kind of moving opposite that, okay? And so if I wanted to just kind of use this side now, well, we can say that the force tension A is equal to Fg1 minus M1A. And now the neat thing is we know A, we know we can find the force of gravity on this first kind of mass here, and we know everything. So now we can just kind of plug in essentially. So force tension A is equal to, well, Fg1. So we're going to have the mass for object 1, 3 point, oh, so let's just leave it at 3, I guess, because we left it at 1 sig fig. 3 kilograms times 9.8 meters per second squared minus, well, the same 3 kilograms times this 3.3 meters per second squared. And when I put that into my calculator, I end up getting that the tension in section of string A is 19.5 newtons. And if I wanted to really round this to my 2 sig figs, because these multiplied, or 1 sig fig, those would round there, I would end up just having, well, it would be 20 newtons really. Okay, so that's kind of our answer there. Now, what if I wanted to find the force of tension over on this section of the string? Well, I would just look at M2 here. Really, that's all I would do. It would be the same steps. We might have different signs. So looking at M2, well, we'd have that the overall, or the net force on object 2, well, now we have gravity is going down, and that's in the positive direction, because positive is this way, right? So I'm going to end up having really my Fg2 minus now the force tension in section B. That's equal to the mass on the second object times its acceleration. And now, since it's actually going to be accelerating still up in this direction, sorry, that was a terrible arrow, it's going to be going up and then over and kind of doing this, well, we're still going to end up having this negative acceleration for it, right? Because it's still going kind of in the opposite direction of motion, so we'll have a negative right here. And so, sorry, I just had a total brain fart, folks. If I'm trying to get this tension, I would end up taking this term and adding it over to this side, and then I would end up just adding over my tension to this side if I want to get it alone. Or you could go ahead and do it a different way. You could add this gravity term over and divide everything by a negative. It doesn't really matter, as long as in the end you get something like force tension B is equal to, well, it's going to be equal to force gravity on object 2 plus M2A. That's the whole idea there. So really, I've just gotten tension alone. I like to think of it as adding this one over here and then adding that one over to that side. But it really doesn't matter how you think about it or kind of look at it, as long as we kind of get it alone in the end. So what this becomes is, well, object 2 is 1 kilogram. So we have 1 kilogram times 9.8 meters per second squared plus, and now we have its same mass again, 1 kilogram times 3.3 meters per second squared. And so putting that one into my calculator here, I end up having 13.1. So we do in fact have, and if we wanted to round it to 1 sig fig, well, that would just be 10, oddly enough, with no decimals. So we can see that absolutely we do in fact have less tension on this side than on that side. Okay. Now, the last thing I want to mention, now that I've done a couple of these, and now that you've kind of seen how we approach this thing, right? Because this is definitely a heck of a lot of a process, right? Is really looking at maybe a couple sample ones. And so, what I would recommend to you actually is I would recommend looking at where did they go? Looking at review problems number 9. You can see it's a 2 mass Atwood machine, looking at number 9. Or if you're feeling a little more ambitious, I think, looking at number 13. Now, keeping in mind that we get to always assume that really in the end, this whole system accelerates together. So if you're finding the acceleration of the 4 kilogram block, that's the same acceleration here and here on the 2 and on the 1. Okay, so that's really it for now on the Atwood machines. I hope that helps.